Okay, hello everyone. In this discussion, we are going to talk about the operational amplifier or simply op amps. So we are going to talk about the structure of an op amp and the application, the characteristics of an op amp. We are going to focus on two specific model, LM324 and LM293. And at the end, we are going to talk about the most popular applications of the op amp and look at the design for those applications. Now, let's start with the basic. Imagine you have a tiny signal. Maybe it's a sound from a microphone or a voltage from a sensor, but it's too small that you can barely measure it. So, and suppose you want to boost the signal so you can actually work with it. Now, that's where the operational amplifier or op amp comes in. The operational amplifier is a high gain voltage amplifier. That means it takes a small difference in a voltage between its two input terminals, amplifies it, and outputs a much larger voltage. Now, we have three pins in an op amp. There is one input which shows normally by a positive sign. We call it a non-inverting input. We have an input showed by a negative sign. We call it inverting input, and the third pin is going to be the output. Now, you might see in the picture that we have a plus and minus V connected to the middle of that triangle. Those are like the VCC sources that basically supplies the power for the op amp. Now, this tiny triangle is a super powerful tool that can basically perform amplification, filtering, mathematical operation, comparison, and even oscillations. Okay, so there are some key applications of the op amps. Like in signal processing, we use op amp to amplify, modify, or clean up analog signals. In filtering, we could have like a low pass or high pass or band pass filter using the op amps. We could run a summation that you can add voltages together using op amp. You can compare voltages and make some decisions. And with some feedback, you can even make an op amp to generate a sine waves. Okay, basically, op amps are like a Swiss Army knife of the electronic. Now, there are some key characteristics in the op amp. Let's talk about it. One is the high input impedance. Okay, so it is like input impedance, this R in, Z in, which is normally is much bigger than 1 mega. It means that op amp draws almost no current from the input source. This is extremely important because it prevents loading the signal source. So if you connect the device with a low input resistance, it would drag down your signal if you don't have this high impedance and basically drain current from that signal source. So basically that input impedance preserves the signal integrity. Another characteristic is a low output impedance. It's almost equal to 0. This is the low output impedance. And basically this allows the op amp to drive heavy loads without dropping the output voltage significantly. In other words, it can deliver power to the next stage in your circuit efficiently. Another characteristic is a high open loop gain. Please pay attention. High open loop gain. The open loop is the emphasis. It is represented basically by the ratio between the output and input. It can get as high as like 200 thousandths as a gain, as the open loop gain. With such a high gain, even a tiny voltage difference between the input terminals can produce like a large output. But remember, in the real circuit, we use feedback to control this gain. Okay, this is open loop gain. Now, we also have two other characteristics, bandwidth and slew rate. The bandwidth basically is how fast an op-amp can respond to different frequencies. It's often given as the gain bandwidth product, okay, which is the gain times the frequency of the bandwidth. Okay, so we call it, this is gain times the frequency of bandwidth. Okay. Another characteristic that we said is a slew rate, which tell us how fast the output voltage can change. Okay, this one can be defined as dV out over dt, okay, which is the normal unit for that is volt per microsecond. Okay, we use that normally. This is very important when amplifying a fast changing signals like square wave or audio. So a low slew rate can cause distortion. Remember that. Now, let's look at the two real world devices, the LM324 and LM293, which both of them are widely used ICs that contains operational amplifiers, but they have different purposes. Okay, so LM324 is a general purpose op-amp. Okay, we call this one quad op-amp. That means it contains 4 independent op-amps in a single IC. The slew rate of the LM324 is normally around like half a volt per microsecond, which is not very fast, but it's good for general analog work. The unity gain bandwidth is normally around 1 megahertz. What that means is at a gain of 1, okay, the unity gain bandwidth equal to 1 megahertz means at the gain of 1, the op-amp can handle up to 1 megahertz. Okay, if the gain changes, the bandwidth changes. Okay, so remember that. We have a maximum output current of 40 milliamp, which is enough to drive the LEDs or logic inputs, but you can drive motors with the LM324. Okay, so that's very important. Now, LM293 is a comparator op-amp. Okay, so this is designed as a comparator. It's not not designed as a linear amplifier. Okay, you can use it, but it wouldn't work properly as a linear amplifier. We have an input offset voltage, which is normally in LM293 is less than a 5 millivolt. That means the comparator can detect very small differences. Okay, less than 5 millivolt. We have a common mode range of 0 to VCC minus 1.5 volt. Okay, remember when we had the op-amp, okay, we connect let's ground this VCC. Okay, the common mode voltage range is from 0 to that VCC, whatever voltage source you have, minus 1.5 volt. Okay, this defines where the input voltage can lie. Basically, this is the range that the input voltage can lie. We have an output type, which is an open collector, which means it needs a pull-up resistor so the output transistor can sink current but not source it. This is what that means, open collector. Now, let's briefly focus on the LM324. It has 4 op amps inside a single package, as you can see in the schematic, in the image, actually, in the left image. That is why we call it quad op amp. We already talked about that the slow rate is a half a volt per microsecond. We have a unity gain bandwidth of 1 megahertz and maximum output current of 40 milliamp. It is simple, cheap, and reliable for basically a starting point working with op amp. Now, let's talk about the actual device and know how to basically the first step of knowing how to work with it. As you can see here, this is actually an actual LM324 would look like. Okay, when you look at that op amp, you would notice a dot at one of the edges of the op amp. Now, this dot shows you how to identify the pins and number them. So the closest pin to that dot is the first pin, and then you can count down 2, 3, 4. I mean, like you can count, but downward 2, 3, 4, 5, 6, 7. And in the other side, you have to count upward 8, 9, 10, 11, 12, 13, 14. Now, look at the 4 op amp. Okay, you see the pin 4 and 11 are that VCC. Okay, all of the op amps use these 2 pin to get powered. So this is the pin 4, this is the pin 11. Now, each of the op amps has its own input, inverting one, non-inverting one, and its own output. Using this map, you can realize which pin is the input of which op amp and which pin is the output of which op amp. So this is important. Remember this, have this in hand so you can know how to work with the LM324. This part is the internal circuit of an op amp. You can see this is like a BJT amplifier. Okay, you don't need to like analyze that or know the detail, but it's good to actually see that at least once. Okay, so now let's now move on to the real amplifier configuration. We are going to start with the 2 most fundamental setups, which is the inverting amplifier and non-inverting amplifier. Okay, when we talk about the inverting amplifier, here's the idea. The input signal is applied to the inverting input, the one that we show it by a minus sign. The non-inverting terminal is grounded. You can see that. Okay, so this is the inverting amplifier. We are gonna have a feedback resistor. Do you remember why? Because we want to control that high gain. Okay, in open loop, we have a high gain open loop without any control. Okay, but with this feedback, we can control the gain. We are gonna have a feedback resistors. This R2 is we call it RF. This R1 is also in here, we call it Rin. Okay, and the voltage gain that we can have for this inverting amplifier, the voltage gain is going to be minus, this is an inverting, minus RF over Rin. Okay, why minus? Because it's inverting amplifier, meaning if you apply a signal, it would shift it 180 degree, and in output, you have the inverting signal in respect to the input. Okay. Now, this setup uses a negative feedback, which means like a hallmark of op-amp stability. Like for example, if that RF is 10 kilo ohm and the Rin is like 2 kilo ohm, okay, now our gain is gonna be -5. Okay, what that means? That means if you have an input of 1 volt, you are gonna have output of -5 volt. Okay, this configuration is extremely common in audio processing and signal conditioning or analog computation. So it's important to know how it works. Now, we said there is another type of amplifier, basic amplifier. We call it non-inverting amplifier. In this one, the input signal is connected to the non-inverting output. Okay? The feedback loop that we use for the gain control is still connected to the -1. Why is that? Because we want a negative feedback so we can kind of like control and make sure of the stability of our circuit. So the feedback is still on negative uh, pin, or as we call it, inverting pin. Okay, there are going to be resistors to do that. Now, the inverting component is also grounded using another resistor. Now, here in inverting amplifier, we call this one RF and this one Rin. Now, you might think, okay, the voltage input is here. Why we call this one that is connected to the ground Rin? This is the point. Voltage is not a single point parameter, is not a scalar, it's a vector. That means voltage is the difference between the potential. I wanted to like show you, okay, the difference between the difference of the potential between 2 points, A and B. So what we call input is the voltage difference between this point and this point. So this is also connected. This is the input, not only this 1 point. Very good. So that's why we can call this one as also Rin. Now, in non-inverting one, we don't have any phase shift. So if we have a sine wave, we are going to have an amplified sine wave here in phase with the input. There is no phase shift. The gain is going to be, the gain in inverting one is going to be 1 plus RF over Rin. What that means? That means the RF and Rin is always positive. We don't have a negative resistance. So this one is always bigger than 0. Okay. Now, that means that the gain in the non-inverting amplifier is always bigger than 1. Okay. So this configuration is very stable and is often used for like buffering or sensory interfaces and voltage followers. Now that basically we covered the theory, let's talk about some amplifiers that are used in real world. Now, inverting amplifier application are like, these are great for signal conditioning, meaning removing offsets or scaling a signal. Analog computation, which is like a summing or subtracting signals in a circuit. We can use it in audio processing, like equalizers and tune control. They normally use inverting stages. Because why? Because they provide a precise control of gain and can invert the signal when we need it. Now, a non-inverting amplifier is normally used in like to buffer the signal, which means giving the signal strength without changing its value. Okay. Uh, it could be used to interface with sensors that like output weak voltages, or build a voltage followers. Like a special case is when RF is 0 and Rin is infinity. Infinity means very, very large. Okay, so basically in that case, the gain become equal to 1. Okay, which means the output is exactly follows the input, but can drive larger loads. Okay, now you can choose the configuration based on the required gain or phase and load condition. Now let's go a little bit deeper on the application. Let's talk about one of the most popular application of the op-amp, which is the active filter design. Okay, filter, let's talk about that first. Filter is a circuit that selectively allows certain frequency to pass through while blocking or attenuating other frequencies. We have low pass filters which allow low frequency to pass and block the high ones. We have high pass filters which allows high frequency to pass and block the low ones. We could have a band pass filters, which in the band pass filter we have a range of frequency that the filter allows to pass. So in band pass we have a mean and max frequency. We have a band stop, which works at the opposite of the band pass filter. We also call it a notch filter, so it blocks a specific range of frequencies. Now, why we use low pass filters? Let's look at an example. Uh, let's say you have a heart rate sensor. The actual heart rate signal is slow and smooth, but it it is contaminated by the high frequency electrical noise that come from the environment. Uh, we want to extract that useful slow signal and remove that fast noises. So that's what a low pass filter does. Now we have passive filters, which uses resistors, capacitors, and inductors. They don't have a gain. We have a limited control over the cutoff frequency because we only design it once and we have to deal with it. This is going to be work unless we change the design. And they have poor performance. Okay, when we talking about the low impedance load. Okay, now active filter, which uses the op amp, they give us amplification. They give us impedance isolation and a precise frequency control. That's very important. So this is why active filters are like a superior in most signal processing scenarios. Now let's talk about one of the most useful filters in electronics, which is the Butterworth filters. There are many type of low pass filters, like Butterworth or like Bessel or elliptic. But when we want the smoothest and most predictable behavior in a passband, meaning no ripple or weird bumps, Butterworth is the way to go. The Butterworth filter give us what called a maximally flat frequency response in the passband. Okay, that means the output signal stays clean and steady for all frequencies below the cutoff. And once it reaches the cutoff points, it starts rolling off in a smooth and predictable way, no surprises. Now, let's look at a first order Butterworth low pass filter. This is the first order Butterworth low pass filter. Well, uh, we have this active filter is more practical version of the low pass filter, especially when we want to control the gain. And as we know, it uses op amp, so Here, what that active first order Butterworth low pass filters look like, as you can see in the picture. We have a resistor and capacitor connected in a way that sets the cutoff points. Now, here we have more kind of like completed circuit, but this R and C basically shapes the cutoff frequency. Okay. Now, then after that cutoff frequency, op-amps buffers the signal and keep it strong. So what is that cutoff frequency exactly? Let's talk about it. The cutoff frequency is the point where the filter starts to reduce the amplitude of the signal. So it's the edge of the passband. Everything below this frequency, when we talk about a low pass, okay, everything below the frequency passes through cleanly, and everything above that starts to fade. Now, we can calculate that cutoff frequency using that R and S, and the cutoff frequency, FC, is 1 over 2 pi RC. Okay, this is the cutoff frequency, which is in hertz. This is the resistor that we talk about in ohm, and this is the capacitor that we have here in farads. Now, this formula tells us where the filter starts to kick in and attenuate the higher frequencies. Now, what actually happens at the cutoff frequency is that at FC, the output voltage is about 70.7% of the input voltage. Okay, so we are talking about the filter itself, not the op amp. Okay, here we have an input for the filter input. Here we have a filter output. The point in a frequency response of the filter that the gain of the filter is like V out, the filter's output over the filter's input. The voltage of the filter input is 70.7%. That is the cutoff frequency place. I'm telling you that so if you have like a gain, you have the frequency response of a filter, but you don't have the actual design of R and C, you know how to spot the cutoff frequency. This 70.7 is equal to minus 3 dB, minus 3 decibel. So if it's in the decibel, you can also know how to find it. Now, like suppose we have a cutoff frequency of 1 kilohertz. Okay, we can pick R if we wanted to like have the FC equal to 1 kilohertz. We can pick a R equal to 1.6 kilo ohm and a C equal to 0.1 microfarad. Okay, and that gives us these two value gives us, if you do the calculation here, FC equal to around 994 hertz. Okay, so it's very close to 1 kilohertz. Okay, now this means below the 1 kilohertz or that 994 hertz. Okay, the signals pass through pretty well, and above that, it gets attenuated. Now, if we plot the behavior on a baud plot, okay, there is something interesting that happens. The gain stays flat. Let's say we have the plot. This is FC. The gain stays flat until we get near the near the FC. Okay, and then it starts to drop. Okay, and like for a first order Butterworth filter, that drop happens at like a rate of minus 20 decibels per decade. Okay, so Decade means here it's logarithmic plot. So minus the rate here is minus 20 dB over the decade. Okay, and it goes very fastly to nearly zero. So it's a very good boat plot actually. That means every 10 times increase in a frequency, this is decade. Okay, every 10 times uh, in a frequency, okay, beyond the cutoff, the gain drops 20 decibel. Okay, why does all this matters? There are tons of real-world application for low-pass filters. Okay, like in audio equipment, they help remove unwanted high-frequency noises. In biomedical device like ECG or EEG monitors, they help clean up the signal. Okay, in power supplies, they smooth out the switching noise from voltage converter. And in a like a microcontroller circuits, they are used to clean up the noisy analog inputs from the sensor, so we have a more accurate readings. So the Butterforce filters are reliable, smooth, and easy to design filters that used everywhere from like music to medication. Okay, I also input the graph for second order Butterworth filter. As you can see, we have two capacitor. This is why we call it second order. Okay, two capacitor means we have two energy storage component. It could be like an inductor in some of the filters. Okay, so two energy storage component. Now we have second order. Now, uh, now that we are stepping into a different kind of behavior for op amps, which means comparators, good, and we are using LM293, the decision making, not like human, more like digital logic, is where the comparators come in. Think of a comparator like a tiny, high speed, basically judges. They don't care how big your voltage is. They just want to know which one is bigger between the two inputs. Okay? Now, comparator uh, compares the two voltages, one on each of the inputs, and it spits out either a high or low signal depending on which one is greater. So how it works is that you connect one voltage to the non-inverting input, okay, and another one to the inverting input. Then the output follows like that. If the positive signal, the inverting one, is greater than the if the non-inverting one is greater than the inverting one, the output goes high. If the inverting one is greater than non-inverting one, the output goes low. So if V in plus is bigger than V in minus, non-inverting, inverting, then output goes high. And if V in inverting one is bigger than the non-inverting one, the output goes low. Now, there is no middle ground. There is no linear behavior. It's just on, off, 1 or 0. Okay? So this is called saturation mode, where the op amps operate as fast, sharp threshold detector. Now, here is something important. In normal amplifier circuit, we use feedback. So we take some of the output and send it back to the input to stabilize things. But in a comparator, we do not use feedback. Okay, no resistors looping back. No negative feedback, nothing. Why? Because the feedback basically tries to balance the output, the two inputs. So it tries to make non-inverting input equal to the inverting input. So that's what gives us to control a smooth amplification. But here we want the opposite. We want the op amp to take even the smallest difference between the non-inverting and inverting inputs. Okay, so we don't want a feedback to make them equal. Now let's peek a little bit inside the LM293. Now, in that LM293, we have a huge internal gain. So somewhere between like 100,000 to a million. So imagine if we have like a non-inverting input, like a millivolt more than a inverting one. Okay, it gives us like 100 volt at the output. Of course, the chip can't actually output 100 volts, but it hits the limit of its power supply. Okay, so what happened is that when the difference is positive, and difference meaning the non-inverting one is bigger than the inverting one, the output simply jumps to the VCC. So this is we say that the gain theoretically is like 100,000 to 1M, okay, 1 million. But in reality, it's capped to the VCC. Okay, so if we have a positive difference, meaning here the output become high, meaning it become equal to VCC. Okay, and if we have a negative difference, meaning the inverting one is bigger than the non-inverting one, the output become low, meaning it becomes zero. Or ground, let's call it ground. That's better looked. Now, the LM293, as we mentioned before, has an open collector output. That means the output pins isn't just a voltage source, it's actually the collector of an internal NPN transistor. So what that means in practice? It means when the internal transistor turns on, it pulls the output directly to GND, to ground, which is a low output. And when the transistor is turns off, the output is disconnected internally, so it floats. So we need a pull-up resistor to bring it up to VCC. Okay, so without a pull-up resistor, the output can't go high. It stays floating. So how we pick the right pull-up resistor, that's important. Okay, let's talk about that. If the resistor is too small, you waste power. Current keeps flowing and heats up things. And if it's too large, the output becomes slow. Okay, because the voltage rises too kind of like slow. Okay, for most logic circuit, a 1K to 10K pull-up resistors work well. So normally our pull-up is somewhere between 1 kilo ohm to 10 kilo. Okay, let's say we have a VCC. Let's do an example. Let's say we have a VCC equal to 5 volt. Okay, and we use our pull-up equal to 4.5 kilo. Okay, now the current through the pull-up become 1.06. So the current become 1.606 milliamp. That is perfectly fine. So it's low enough to avoid heat, but it's fast enough to basically switch the logic. Now let's actually build that. But wait. Okay, so what if the temperature is hovering near the threshold? Okay, so the comparator might keep switching on and off rapidly because of a tiny fluctuation. That's where hysteresis comes in. We add a resistor from the output back to the non-inverting input that creates a tiny positive feedback loop. Okay, so now we get two thresholds, one for turning on, one for turning off. Okay, now finally, let's review the key aspects of the LM293. The input offset voltage is less than 5 millivolt. The input voltage range is 0 to VCC minus 1.5 volt. The output type is open collector. Supply voltage works from 2 to 36 volt. Okay, and output sink current can pull up to like 20 milliamp to the ground. Okay, now let's talk about another application of the op-amp, which is the oscillator. We are going to talk about the vein bridge oscillator in this example. Imagine you want to generate a perfect sine wave just from a power supply. So we don't have an input signal, we don't have a waveform generator, nothing but a little circuit that sits quietly and creates like a smooth, continuous oscillation all by itself. Now that's the job of an oscillator. And among all the oscillator design, one of the most elegant and intuitive one is the vein bridge oscillators. Now let's break it down step by step. What is an oscillator? In electronic, an oscillator is a circuit that takes DC power as an input and produce a repetitive waveform at the output. Okay, the waveform can be a sine wave or a square wave or triangle or sawtooth. Okay, now the vein bridge oscillator specializes in generating a clean sine waves. So it makes it ideal for audio tunes or signal generator and test equipment. Now, why use the vein bridge oscillator? Here's why the circuit is so widely used. It produces very low distortion and a stable sine wave. It's easy to build with just an op-amp and a few resistors and capacitors. And you can easily adjust the output frequency using the RC values. And it works well in the audio range. It could be from few hertz to hundreds of kilohertz. Okay, so if you're designing anything from a tune generator to like a lab test circuit, this is a go-to option. Now, what makes that oscillation happen? To make any oscillator work, you need to feed part of the output back into the input, but not just any feedback. You need a positive feedback. Okay. This is very different from amplifiers where you use negative feedback to keep system stable. Now, we want the system to sustain a repeating signal. So we give it a push that reinforces itself. There is a fundamental rule called Barkhausen criterion. And it tells us the two conditions for sustained oscillation. One is the loop gain, meaning the gain from input through the circuit back to the input, it should be equal to 1. Okay? the total phase shift around the loop must be 0 for full 360 degrees. Okay. Now, the vein bridge oscillator is special because it meets both of these conditions at one precise frequency. Now, the core circuit is an op-amp like LM324, okay? A series RC network, you can see here, in the feedback loop, that it sets the gain, and potentially a nonlinear element like a lamp or diode or JFET to stabilize the amplitude and prevent distortion. Now, how we could calculate the frequency? Okay, the frequency of the sine wave, let's call it F0, okay, F of oscillation, is set by the two resistors and two capacitors that form the vein bridge. Okay, if the resistors are equal and the capacitors are equal, okay, the formula, okay, these are the capacitors and resistors. You can see these are so far they are equal. The oscillation frequency become 1 over 2 pi RC. Now, R is the resistance value in O. Okay, so C is the capacitive value in farad. So as long as the value are matched, this formula gives us the exact frequency at which the circuit will oscillate. Okay, now how it works is the input RC network, which is one resistor and one capacitors, cause a phase lead. So signal shifts forward. Now the feedback RC network causes a phase lag. So the signal shifts back. At one specific frequency, these phase shifts cancel each other out, giving a total phase shift of the 0. If the gain around the loop is exactly right, the op-amp sustains a clean sine wave forever. So basically, the circuit is delicately balanced, just enough gain and just the right timing to maintain the continuous oscillation. Now, to keep the waveform going, the loop gain must equal to 1. We already mentioned that. That means the op-amp must have a closed loop gain of 3. Okay, so AV, which is equal to 1 plus RF over R in, RF, R in, should be at least 3, meaning that RF or R in should be at least 2. Okay? Now, you usually start with a gain a bit higher than 3, so it helps to start the oscillating. Then a stabilize mechanism kicks in and brings the gain back down to exactly 3. Okay? If the gain stays too high, the sine wave will clip. It becomes flat topped and distorted, like a square wave. If the gain is too low, the signal dies out. So we need a way to dynamically control the gain. Now, we have 3 common methods. One is lamp stabilization. Okay, this is a classic analog trick. We place a small incandescent lamp in series with the RG. Okay, so as the output sine wave grows, more current flows through the lamp heats up and its resistor increase. That reduces the gain and stabilizes the amplitude. Okay, we could have a diode limiting, which is another method. We add 2 diodes in opposite direction across the feedback or the input. When the voltage exceeds the diode threshold, which is about 0.7 volt, the diodes conduct and clamp the signal. Okay, so it's simple, effective, and like a solid state. We can have like a JFET or basically JFET or MOSFET as like a variable resistor. So by adjusting the gate voltage, we change the resistance of the JFET in real time, which adjusts the gain. Okay, now let's build one actually. Suppose we want a sine wave over like the f of oscillation equal to 1 kilohertz. Now, let's first pick the capacitance. We pick the capacitance as 0.1 microfarad. Now, using that formula, that means this formula. That means the R is going to be 1.9 kilo. 1.59. Okay, so which we call it, let's call it 1.6 kilo. Okay, now for the gain, we need the RF over RG or Rin to be equal to 2. I'm using different indexes because in different textbooks you use different indexes. Okay, so I want you to understand and not get confused when you read different textbooks. So if we choose this one as 1 kilo ohm, okay, that means the RF is going to be 2 kilo. This is as simple as that. Now you have your circuit and it works. Now, after you build that circuit, you can connect the output to an oscilloscope, power it up, and watch the waveform. Okay, so if everything is working, you'll see a smooth sine wave. The frequency will be stable and the amplitude will hold steady. Now, if the gain is too high, the waveform becomes clipped. So you may see some harmonic distortion. And if the gain is too low, the waveform slowly dies out. So the output fades into oscillation. Okay? Now, final thought. The Wayne bridge oscillator is perfect blend of the mathematics, physics, and engineering. With just a few components, you actually create a waveform. Okay? And whether you're designing a lab tool or like a tuning synthesizer, you'll come back to this oscillator again and again. So this is the very important component when we talk about the signal processing and all like electronic. Now, let me know if you have a question. We are going to move on to the actual assignment of how we can deal with the op-amp, how we can measure the characteristics, and how we can actually create an actual amplifier or oscillator comparator. Thank you.
Okay, now that we know how the op-amp works and what are the application and we went through the theory, let's talk about how we can measure the slow rate in the laboratory. Now, we already mentioned an op-amp had 3 main signal port and 2 power supply port. Okay, we have non-inverting input, we have inverting input, and we have output. We have a port that we connect to the VCC and the port that we connect to ground. Okay, so this one is actually the positive and negative port of our voltage supply, our power supply. And normally the VCC is somewhere for LM324 is somewhere, let me write down that. This is LM324 is somewhere between 3 volts all the way to 36 volts. Okay, we don't want to go near that top or bottom interval. Okay, so somewhere in between. Now, an actual LM324, as we saw before, is look like that. Okay, we have a dot in one of the edges, This is for, as we mentioned, for recognizing and identifying which port is which. Okay. From the dot, the first pin is gonna be, this is 4 op-amp. Okay, you wanna to use one of them. The first pin is gonna be the output of the first op-amp. The second one is the inverting input of the op-amp. The third one is the non-inverting input of the op-amp. And the fourth pin is going to be the port of VCC. Okay, now if you count down 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, 11, okay, the 11th port, okay, which is the middle port of the other side of the LM4, is the port that you connect to the ground. Okay, now we want to calculate the SR, slew rate, which defines based on the change in the output voltage. This is output voltage divided by the time that takes that change, the time that op-amp takes to actually do that change in the voltage. Okay, in order to measure the slew rate in our laboratory, we are going to use a unity gain buffer op-amp. Okay, so this is unity gain buffer. Okay, we are going to use this configuration of op-amp in order to measure the slew rate. It's not a very kind of like complicated system. So we have our op-amp, VCC and ground is already known. We inject the input to the non-inverting input, and we are gonna connect the output as a feedback without any resistance, is a direct feedback to the inverting input. Okay, and we are gonna measure the output here. Now, what we expect is that if, for example, we have a high speed changing input, like, for example, in this example that I draw, is a square wave, okay? The blue curve is the input, which is the square wave. The op-amp cannot immediately take the change and apply it to the output. So there is a gradual voltage increase and decrease, okay, when it's identify any rapid changes in the input, okay? The slope of this change, which is the amount of the voltage change from 0 all the way to the peak voltage, this is delta V, and over the time that it takes the op-amp to change the output from the lower level to the steady state top level, this time, this ratio is going to define the slew rate. Okay? Now, if you measure one slew rate, like a rising slew rate, that's enough. But to make sure and have a good picture, it's better to have both rising and falling edge slew rates in our measurements. Like, I have like an example, like if we have a 1 volt of change in output, so it changes from 0 volt to 1 volt, okay? And this change happened, for example, in 2 microsecond, then our slew rate is 1/2 microsecond, which is half volt per microsecond. Okay? Now, let's say we wanted to like measure the falling edge too. We have the same level of delta V because we are going from the top voltage, the 1 volt, all the way to the 0. So the delta V is still 1. Okay? But let's say the duration of this change is different, for example, with the rising edge. Normally happen that. They are very close to each other, but they are not absolutely equal. So let's say it's 2.1 microsecond. Okay, it's slightly higher than the rising edge. then our slow rate becomes 0. If you do the math, becomes 0.476, okay, volt per microsecond. So this is how we could measure the slow rate of our op-amp. Now, remember, we need to use a unity gain buffer, meaning the input goes to the non-inverting pin, and we are gonna have a direct feedback connecting the output to the inverting pin. And then we are gonna measure the output. Okay, this orange curve that I said, that I drew here. Okay, so let's go to the lab and actually measure the slow rate of an actual LM324.
Okay, we are in the lab, and as you can see, I already create the unity gain buffer with the LM324. I connect the VCC and ground to a 12 volt, around 12 volt. Let me fix it a little bit. Okay, 12 volt VDC, and I'm using the function generator to apply a square wave with the frequency of 1 kilohertz. This is the amplitude is 4, and I shifted 2 volt DC, so it changes from 0 to 4 instead of -2 to +2. And I applied that, and I'm using the oscilloscope. The channel 1 would detect the input, as you can see, is a square wave, and I zoomed in for the calculating the slow rate. And the channel 2 is the output. As we said, this is a unity gain buffer, so you have to short circuit the output and the inverting input, and use the non-inverting one to apply to inject the signal to the op amp, and then we use the measurement. Now, before I talk about this measurement, I choose another type of LM324. And the reason is that like some of them doesn't have that dot that we talk about at the edge, so you can basically follow the previous one. Now, on this model, as you can see, there is another aspect. If you can detect this dip in the surface of the op amp, okay, this is another indicator to identify the pins. If you uh, 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 hold the op amp in a way that this dip facing up is the upper edge of the op amp, like this, okay, then you can start numbering the pin in a way that the when you face that surface, the left top pin is the number 1, and you can count 2, 3, 4, 5, 7 here, and then go to the other side, 8, 9, all the way to the 14, which is the top right pin in your circuit. Okay, so for example, in our system, we want one of the op amps, so we are going to use these 3 pin, 1, 2, and 3. The first pin is going to be the output of that op amp. The second one is the inverting, that V minus, the inverting input. The third one is the non-inverting input, the V plus, where we inject the input, the square wave. And as we said, unity buffer means we have to short circuit the first and second pin. And the fourth pin is VCC. Now, the 11 pin, which is 8, 9, 10, 11, the middle one and the right side, okay, is ground. So you have to connect the fourth and the 11, the two middle pins. The right one goes to the left one goes to the VCC, the right one goes to the ground. And then you have the unity gain buffer for the one of the op amp in the LM324, which contains 4 op amp, to basically do the experiment. Now, I already, as I said, set everything, and you can see that I measured the output and input. it is visible that the output gradually increase until it gets to the a final value. Now, you can basically measure that by using the units in your grid, in your oscilloscope screen, and the time division that you defined in your oscilloscope. Okay, now if I wanted to like count down, I could count two line within 1 unit. Okay, it's like 40% of 1 unit of the grid. 40% of 1 unit. Okay, now it's 40%, and each of the unit based on my setting was 5 microsecond. So 40% of that 5 microsecond become 2 microsecond. So in this example, it takes 2 microsecond for the voltage to go from 0 to the final value. And for the final value, I have 1.5 unit, and my voltage division is 200 millivolt. Okay, so what I'm getting an output is 300 millivolt. So let's calculate the slow rate. I have, is that correct? Yeah, I have 200 millivolt, which is zero point 0.2, divided by 2 microsecond, which is the slow rate of this op amp is 0.1 volt per microsecond. Okay, so this is how we could measure the slow rate. You can also measure the slow rate for the falling edge, which I don't have. Let me have this, hopefully. Please. I want to measure the come on. Okay, now it's good. Let's zoom in. Come on, come on, come on, come on, come on. Go to the middle. Zoom in more, zoom in. Now, okay, you can see that still we don't have a precise like an instant change in a output. And you can see there is a shift, there is a delay also. This is also count on the slow rate. So as you can see here, I have more duration of the time since the edge of the input until the output gets to the final value. It is still 1.5 unit of my volt division. I still am in the 200 millivolts, so it's 300 millivolt. Okay. And did I measure? Did I calculate it? The first one is I think I used 200 millivolt in my calculation in the raising edge. So forget about my error. You do the right thing. Okay, so you do your measurement. So this is 300 millivolt, and the falling time is 60%. Now it's 60% of 1 unit, which is still 5 microsecond. So now I have 3 microsecond as my delta T. So delta V is 300 millivolts. Delta T is 3 microsecond. So it's become 0.1 volt per microsecond. Before it was low. It was lower. Right? No, it was higher. Okay, it was higher because 300 millivolt over 2 microsecond would be 0.15. Okay, so rising edge was 0.15 volt per microsecond. The falling edge is 0.1 volt per microsecond. So it's slightly different, but close to each other. Okay, so this is how you can basically measure your slow rate in your op. Let's move on to the next concept.
Okay, let's talk about how we could design an adjustable amplifier, okay? Meaning we have adjustable gain using for an amplifier using the op amp, okay? So as you can see, we are gonna use a non-inverting amplifier for this example. And in our circuit, you can see we have the amplifier, which is supplied by VCC, okay? We are gonna inject the input to the non-inverting terminal, the positive one, and we are gonna use the non-inverting one to connect the feedback through a potentiometer, an adjustable resistor. So we are gonna feedback the output to the inverting terminal, the -1, using the adjustable resistor or potentiometer. And we also gonna connect the non-inverting port to the ground using a resistance named ground resistance, RG. Okay, now you can use the RG as an adjustable resistor as a potentiometer and have like a constant resistance and feedback. I'm using this because of my supplies and my inventory in the lab, so this works better for me. Now, as we know, the non-inverting amplifier gain is going to be 1 plus the feedback resistor over the ground resistor. Okay, so you can see by changing the denominator in this equation, in this part of the equation, we are going to change and adjust the gain. Now, when we talk about the actual amplifier, which is LM325, let me write down, we are going to use LM324, sorry. We are going to use one of the amplifier. I chose the first one. And so we are going to identify the pins so we know which one is the input, which one is the output, which one is the feedback goes to, and the ground connect to through the ground resistance. Now, again, when you have the LM324, there is a curve here, there's a dip here. You need to point the dip upside. Okay, if you look at that amplifier in this configuration, the left part, it sometimes is noted by dot. The left side, okay, will start with the pin number 1 in the top. So the left top pin is number 1, and then you can number them from top to bottom. So 1, 2, 3, 4, 5, 6, 7. And the right side is going to be numbered from the bottom to top, 8, 9, 10, 11, 12, 13, 14. Okay, now, as we said, we are going to use the first amplifier. So we know the first pin, the pin number 1, is going to be the output of this amplifier. The pin number 2 is going to be the inverting terminal of the amplifier. The number 3 is going to be non-inverting terminal of the amplifier. The pin number 4 is the one that we use to connect it to the VCC for supplying the amplifiers. So pin number 4 is connected to the VCC, and pin number 11 is going to be connected to the ground. Okay, so what's happened here is this is pin number 4, this is pin number 11, this is pin number 3, pin number 2, and pin number 1. Okay, now, normally, when we talk about the gain of amplifier, the gain is given to us in a decibel unit. Okay, now let's talk about what it means to have a gain in decibel. Gain in decibel is actually 20 times the logarithm of the gain, the actual like a scalar gain, okay, in root of 10. Okay, so this is the formula to calculate the decibel gain from the AV, the voltage gain that we have. Now, the reverse part is going to be the AV, the voltage gain, is going to be 10 to the power of that decibel divided by 20. Okay, now let's actually do a design using this adjustable amplifier circuit that we have. Now, in our assignment, we want to design an adjustable amplifier that the gain would change from 12 to 32 decibel. We are going to input a 200 millivolt AC signal, which is going to be a sine signal, a sine wave, with the frequency of 1 kilohertz. Okay, so what is our input? 200 milli, okay, times sine of 1 kilohertz times t. Okay, so this is omega. This is the amplitude. I have, as I said, I have a limitation in my inventory. Okay, so the way I'm going to do that is that I'm going to set one of the resistors, this constant resistor here, to one of the resistors that I have actually in my lab. Okay, and then find the values for feedback resistor. Okay, the resistor that I have is 170 ohm resistor. So I'm gonna set my RG to the 170 ohm, which is very low. Okay, in reality, you wanted to like keep this as a high number, like a kilo resistor. As I said, the reason that I'm not going to the kilo ohm is because of my inventory. But in reality, when you want to design the actual adjustable amplifier, it's better to have a bigger RG. Why is that? Because if you have a bigger RG, this resistance would dominate the circuit, the internal circuit of the op-amp. So you don't have a sensitivity to noise. You don't have the sensitivity to the variation caused by the thermal and temperature kind of like change. So it's better, in order to have a more stable result, to have a high ground resistance. I don't have this luxury of choosing that, but so I choose the RG based on my inventory, 170 ohm. Now, I want to have the minimum gain of 12 decibel. 12 decibel means that my AV is going to be 10 to the power of 12 over 20, which is somewhere close to 3.9. I'm going to consider that. I'm going to consider the minimum gain, the AV minimum, as 4. Okay, I'm going to round it up. Okay, so 4. My maximum, I mean here, my maximum gain is going to be 10 to the power of 32 over 20, which is going to be somewhere around 39 something. Okay, so I'm going to round it up and call my AV max equal to 40. Okay, now that I know the minimum gain and maximum gain, I can use this formula of the gain, in order to find what is going to be my resistor in feedback. Now, let me erase these equation, open up some space. So my AV is going to be equal to 1 plus the RF over RG. So for the minimum, 4 is going to be equal to plus 1 over RF of the minimum gain over Our RG is 170 ohm. Okay, so basically our feedback resistance for minimum gain is going to be, let me calculate that. And what is it? Which is going to be 510 ohm. So this is my feedback resistor for the minimum gain. For the maximum gain, this one is going to be 40. So it's going to be 1 plus the resistance feedback for a maximum gain over 170 ohm, which means, we calculate that, which means that my feedback for the maximum gain, feedback is for maximum gain is going to be 6.6. Let me actually be more accurate. 6.63 kilo. So I have these two resistors. So if I adjust my circuit, so this one is 170 ohm, and I use a potentiometer. If I set my potentiometer in 510 ohm, I expect to get a gain equal to 4, meaning if I have a 20 millivolt peak to peak, okay, this is peak to peak, in okay, if it's peak to peak, that means this one is 100. 200 millivolt peak to peak, and the gain is 4, I expect the output to be equal to 800 millivolt peak to peak. And if I wanted to have like a 4D as a gain, that means I expect my output to be 8 volt. Okay, so here I'm gonna get the output of the out of 800. This is peak to peak millivolt. Here I'm gonna get the out peak to peak equal to 8 volt. Okay, now let's actually go to the lab and see if our experiment would be consistent to the design that we had here.
Okay, let's talk about the actual experiment. Okay. I already built up my circuit, so I have the LM324 here. This is my output, okay, which I'm gonna measure. The second one is my inverting port, and the third one is my non-inverting. I connected the VCC to the 4 and ground to the 11 port. I'm using 170, as we said, or to ground the non-inverting, sorry, to the invert, so to ground the inverting terminal, and I'm gonna use a potentiometer to connect the output to the inverting terminal as a feedback. Now, since I want the maximum resistance for the feedback as 6.63 kilo ohm, I chose a 10K potentiometer. Okay, so now let's set our system. So I'm gonna connect the input and also connect the VCC to my circuit. I am gonna use the channel 1 to measure the input, so I know what's going on in my circuit. So this is gonna be the input. Now I am gonna use channel 2 of my oscilloscope to measure the output. Come on, come on. Okay. Now, here I'm gonna use a sine wave. You can choose the wave in the in the signal generator, sine wave. It's already in 1 kilohertz frequency, so I want to change it. Let me go a little bit higher. Now, the amplitude, as I said, I want 200 millivolt peak to peak. Okay. Now, if you remember, we said that the op amp works with when there is a fully positive voltage applied to the input. It's because of the transistor inside the op amp. Okay, so this currently this sine wave have a half positive cycle and half negative cycle. In a half negative cycle, my op amp is not going to be activated, meaning it's going to cut the negative half. So what I have to do, offset the whole sign. So I'm going to offset for 100 millivolt DC. So I know on every time I have a positive value in input. Okay. Now, again, I'm expecting somewhere the voltage somewhere between 800 millivolt all the way to 8 volt. Okay. So if you remember, let me disconnect the VCC before I start that. If you remember, we said the op amp range of the output voltage is VCC minus 1.5 volt. Okay, so what I have to do, okay, what I have to do, okay, now let's build that amplifier that we designed, okay, and as you can see, I already connected the circuit. I have the LM325 here. I connected the 4th pin to the VCC and the 11th one to the ground. Now I'm going to use the non-inverting pin, which is the 3rd pin, as an input. It's connected to the input. And I'm going to have the inverting one connected to the ground through that 170 ohm that we talked about. I am going to feedback the output, which is the 1st pin, using a potentiometer to the inverting terminal. Okay, so because I want a resistor in a range of 500 ohm all the way up to 6.63 kilo, I use a 10K potentiometer. Okay, so the max of this potentiometer is a 10 kilo. Now, I use the channel 1 to see the input in my oscilloscope. Let me turn it a little bit. And channel 2 for the output. Now, let me connect the input signal to my circuit. This is connecting the input. And now, remember, let's talk about the input signal first, and then I'm gonna give you another point. We said we want a sine wave as an input with 1 kilohertz of frequency, 200 millivolt peak to peak. Okay, now, as you can see, I have an offset here. I hope you can see that. An offset of 100 millivolt. Okay, the reason is that op amp input needs to be positive so they could trigger the transistor inside the op amp. Okay, so if you don't offset that, okay, somewhere in the cycle you would have a negative voltage. Okay, that means on that negative part, your op amp is going to be deactivated. So it's going to be chopped. The signal is going to be chopped. Okay, so I offset the 100 millivolt. So I make sure that through the time, I never go below the 0 line. Okay, now this is 1 aspect. Another one that I wanted to mention is that we already talked about that in the theory part, that the maximum output and actually the range of output that you can get from an op-amp, especially LM324, is from 0, okay, all the way through the VCC minus 1.5 volt. Now, I'm expecting somewhere between 800 millivolt all the way to 8 volt. So that means my VCC should be at least 9.5 volt. Okay, now I'm going to be more conservative. I'm going to go higher. So I actually set that to 20 volt. It doesn't matter. You can go all the way down to like 10 volt. Okay, that's okay. But I'm too conservative, as you can imagine. Okay, now let's apply the input. Okay, and connect the VCC to our circuit so we could supply the op amp. And power the system. Okay, now you can see first I wanted to show you how it works. This is our output. The voltage division is in 200 millivolt. That means the whole signal, input signal, will gonna occupy 1 unit of one of the grids of our oscilloscope. Now, if this is the output, and the output signal, let me change it, the output to the 200 millivolt. So it would be same as the input. Okay. Now, right now you can see that because I am in a very high gain. If I change the gain, you can see that my output is getting lower and lower. So by adjusting the potentiometer, I can adjust the gain, and you can see that the output is going like right now. Okay, right now, this is the output of 4, right? 1, 2, 3, 4. Now, this is 4 times the voltage division is the same. So right now my input is 200 millivolt peak to peak, and my output is 800 millivolt peak to peak. Let me be more precise. It's a little bit lower than 800 millivolt. Come on. Okay, now it's 800 millivolt. Okay, now based on our calculation, the potentiometer for having a gain equal to 4 should be 510 ohm. Now let's measure. I am gonna, where is my cables? I am gonna disconnect my potentiometer, and I am gonna see what's happening. Where is the other port? Okay. What's happening in my potentiometer? Now, as you can see, right now my potentiometer is in 5050. Close enough. We needed 510. But 505 now giving us the amplitude gain of 4. Now, let's go for the next part. Connect the potentiometer back. Clean up a little bit here so we know what's going on. And inject the output. Now, I want a voltage equal to 8 volt. So let me change my voltage division to, let's go for 2 volt. Okay. Now I'm going to apply my signal, and I'm going to go higher until I get the 8 volt. So now this is right now the output is 8 volt. The input is still 200 millivolt peak to peak. My output is 8 volt peak to peak. This is what we wanted when we said we want to gain of 40. Now that we have that, let's see what is gonna be our potentiometer. Again, I am gonna measure my beautiful potentiometer. It's a little bit more than I expected, the difference. So right now I am in 5.19 kilo, and it gave me that 40 gain. Okay, so right now you see how the potentiometer can adjust the gain in our voltage. Now I wanted to show you something. Now we said this is 8 volt. Oh, it's not 8 volt. Sorry. Let me check again. This is now 8 volt. Hopefully we are good. Now, it's still the same. It's 5.2K. It's a little bit the error, the difference is a little bit more than I expected, but you never know. It's a reality. Now, what I wanted to show you is that if I have my output, but my VCC is lower than I expected. Now, this is the 8 volt, so I need at least 9.1. Okay, so let's go down. Now I'm at 10. Look at the output. 9.5. And if I'm going lower, you can see that now my output is clipped. Okay, let me go lower and you can see it better. See? So this is how it works. Now, let's talk about the input. I said there is an offset. Now, I'm going to change my offset to 0. Okay? Now, you can see that because I have negative half cycle, it gets chopped down. This is the point that the input crosses the 0 line. So this is what we meant when I said, like, okay, you need to have always a positive voltage in your input, and your supply should be big enough to support the voltage that you wanted. Okay, now let's move on to the next.
Okay. Now let's talk about how we can build an integrator out of the op. Now, as you can see for the integrator circuit, we have our op-amp. We are going to connect the input through a resistor to the inverting terminal. We are going to ground the non-inverting terminal. Of course, we have VCC to supply the op-amp. And we are going to connect the output through a capacitor into the inverting terminal. Okay, now let's talk about how this type of circuit, this schematic would work as an integrator. The current that goes into our circuit, if you use the Ohm law, is going to be the input voltage minus the inverting terminal voltage divided by the resistor. Now, if you remember, when we talk about the op-amp, we said between the two terminal, inverting and non-inverting terminal, we have a very high impedance, let's say ideally infinite. Oh, okay. So if this is infinite ohm, that means we don't have any current passing between the inverting and non-inverting terminal. What that means? That means we don't have any voltage drop across this impedance. And since we connect the non-inverting one to the ground, so the voltage here is 0, there is no voltage drop here. So this voltage should be 0. Okay, what that means? That means the voltage across that resistor is going to be input voltage. So the current is going to be the voltage of input divided by the resistor. Now, let's talk about the capacitance. Again, this is 0. So the voltage across the capacitor is equal to the output. Okay, now the current passing through the capacitor, as you know, is equal to the capacitance times the differential of the voltage across the capacitor in respective time. So I is equal to C dV out over dt. Now, these two equations are equal to each other because this is the same I. Why is the same I? We said, run a KCL here. There is no current passing through between the terminal. So all the current that goes into the circuit will pass through the capacitor. So these two currents are going to be the same. Now, if they are the same, that means input voltage over the R is equal to the C times the differential of the output voltage in respect to time, of course. So it's obvious that V out in time domain is going to be minus 1 over RC, the integral of the input voltage in time. Now, you might think, okay, we don't have any minus here, where this minus came from. Remember, when we use the inverting terminal for the input, we already talked about that. Whatever is in the output is going to be 180-degree phase shifted from the input. So that minus came from that 180 phase. Now, let's talk about an example of how we could design an integrator. Okay. What we have, a specific example is that we want to have a square wave with 2 volt peak to peak as an input, and the signal has the frequency equal to 1 kilohertz. Okay, so this is our input. That's me with another color. This is going to be our input. Okay, this is the time period of 1 cycle, and this is 2 volts. Very good. So to be precise, this axis is the voltage, this axis is the time. Now, this is our input. If we integrate, like mathematically, the integrate of this input is going to be a triangular wave okay, that ramps up when we have a voltage and ramps down when we don't have a voltage. Okay, so we expect to have this kind of like situation between the input and output. Now, let's see how we could actually design this circuit, the values of the capacitor and resistor, in order to get something like that. Now, we said the frequency is 1 kilohertz. That means the time period is 1 over 1 kilohertz, which is 1 millisecond or 0.001 second. Are we good? Now, we want, as you know, let's talk about that. As you know, if we have a capacitor or inductor in our circuit, that means we have a transient parameter named time constant that defines the behavior of this circuit in respect to the changes in the input. Okay, now for the RC circuit, the time constant tau is equal to R times C. Now we want to match this tau with our time period. in order to have a proper integrator. So R should be equal to T, meaning 0.001 second should be equal to RC. Now, we choose an R, this is easy. We choose a specific R for our circuit. I'm going to say R is equal to 10 kilo ohm. Okay, now we are going to use this to calculate the what kind of capacitor, what value of capacitor we want. Why I chose like this high number for the resistor? Okay, the reason is that I don't want to draw very high current from my source. Okay, that would kind of like deviate the performance of our source. Now, if the R is 10 kilohertz, that means using this equation, the capacitor, if you do the calculation, the capacitor should be 0.1 microfarad. Are we good? Now we have all the value. We have the value of capacitor. We have the value of resistor. We know the input. So we expect the output to be such a triangular wave. Okay. Now you can imagine if I change the duty ratio of this square wave, meaning the on time, okay, the percentage of the on time in respect to the whole one cycle time period. So let's say I chop the voltage earlier, okay, lower duty ratio. What I expect from the integrator is that I have a higher ramp and for the rising part of triangle and the lower slope for the falling. And if I go higher in the duty ratio, that means I have a lower slope of rise time and higher slope of fall time. Are we good? Now let's go to the lab to see if it actually what we have in the lab is actually meets our theory and our design. Okay, let's talk about the actual experiment. Now, I already built up the circuit. So I have my LM324, okay? I connected the inverting port through a 1 kilo ohm resistor to the ground. And I have a capacitor between the output and the inverting point. And I grounded the non-inverting terminal. Okay, now I am going to inject the input through that resistance to the inverting terminal, and I'm going to measure the output. So the first channel in my oscilloscope measures the input, and the second channel, the blue one, measures the output. I have a square wave in my signal generator with 1 kilohertz of frequency, 2 volt of the peak to peak. I am going to inject it. So far, I didn't turn on the op amp, so it's easy to see that, okay, it doesn't integrate right yet. Okay, so this is my input. Now, if I turn on my op amp, you can see that this circuit is actually integrating the signal. Now, you might think that, okay, in theory, the integrate of a pulse, as we talked about in theory, okay, is that in the positive signal, in the positive part, we should ramp up, and in the negative part or the zero part, we should ramp down. But why it's different? That's come from that 180 phase shift that we talk about. Okay, so this is actually ramping up and ramping down, but we have 180-degree phase shift, so it's moved half a cycle toward, like shifted half a cycle forward. So now you see the decreasing slope
in the on part and the increasing slope in the low voltage part. Okay, so now we already talked about the duty ratio. Let me change the duty ratio. Right now I'm in 50%. I am gonna change it to the 30% to see what's gonna happen. You see, let me bring down the integrator. You can see that I have a very sharp slope. Okay, I changed the duty time. That's why you don't can't see the difference, and it seems like it's softer slope, but it actually increased. And now, in reality, you can see that we have actually a lower slope in our negative part, but since the negative part is too long, okay, that means the integrator is already reached, the integral is already reached a very low value, okay? It's reached a very low value. So it's already is close to zero. That's why you see a flat line. Now, let me change the amplitude. Hopefully we can see. Let's go for 5 volt. Now you can see that now the integrator would not get very fast to zero. So now we have still we have, you can see we have a lower slope in our off time and a higher slope in our on time. Now, let me change the duty cycle to 70%. Okay? And let me tune my oscilloscope better way. And I am gonna lower my voltage. Now you can see the reason that I lowered my voltage is because of the limit in my op-amp. Okay, so you can see now we have a slower slope in our on time when the duty cycle is increased and a higher slope in our off time. So this is how it works. Okay, now you can obviously see that there is a jump here. It doesn't connect. I want to make another point when we talk about the RC circuit. And this part is because we have a slightly different capacitance and resistance in our circuit in reality. So the tau is not exactly matching our frequency. So it takes more time for the capacitor, okay, to get discharged or basically integrate. So that's why before it reaches the zero of the integration, okay, we inject the input high value, and that's why there is a jump here. Now, okay, let's move on to the next concept and next experiment and see how we can use op-amp to build an active filter.
Okay, now let's talk about creating an active filter. In this example, we are going to talk about a Butterworth's second order active filter using an op-amp. Now, as you can see, the circuit for a second order filter, and we are using a LM324 also as an op-amp, okay, is as you see like here. So we have a schematic. We are going to inject the input, okay, through two resistance, R1 and R2, into the non-inverting input. So it's going to be connected to the non-inverting terminal. Okay, let's talk about how we can design a second order filter, active filter using an op-amp. Again, in our example, we are going to use the op-amp model LM324, which is a general op-amp. As you can see, this is the schematic for Bauer-Worst second order filter. Okay, now in this schematic, you can see that we are injecting the input through the R1 and R2 resistors into the non-inverting terminal, the positive one. Okay, let me make it clear. This is the positive non-inverting terminal. Now, we are going to connect the non-inverting terminal to the ground through the C1 through a capacitor. Okay, and we are going to feedback output through another capacitor C2 into the point between the two resistors. Okay, now the non-inverting the inverting terminal, the -1, the inverting terminal, is connected to the ground through a ground resistor. And we also have a feedback through a resistor from the output to the inverting terminal using the feedback resistor. Okay, this is the schematic of the second order filter. Now, let's talk about the math behind it. The transfer function of a second order filter is going to be 1 over 1 plus 2 psi times S over the omega C, omega of cutout frequency. This is the cutout angle of frequency, plus S over omega C squared. Okay, now this S, when we talk about the sinusoidal input, which is what we are going to inject in our circuit, is going to be equal to J omega. Okay, which, as you know, the angular frequency is 2 pi the frequency, so it's going to be equal to J 2 pi F. Okay, this F is the input frequency. The omega C, which is the angular cutout frequency, is going to be again equal to 2 pi the cutout frequency that we want to design the filter for. Okay, and the psi 4 watt-hours is 1 over square root of 2. Okay, now this is our transfer function. Our cutout frequency is going to be based on the RC circuit that we have, is going to be 1 over 2 pi the square root of R1 times R2 times C1 times C2. Okay, you can go through the circuit analysis and electrical circuit theory to see why the cutoff frequency of these RC second order circuit is 1 over 2 pi square root of R1, R2, C1, C2. Okay, I'm not going to discuss that here. Now, in our system, we normally consider R1 and R2, and we set that actually equal to each other. Also, we set C1 and C2 equal to each other. So if we do that, mathematically, this is going to be R squared, this is going to be C squared. So eventually, the cutoff frequency would become 1 over 2 pi RC. Okay? Now that we say all the mathematics behind this second order filter, let's design our filter for the cutout frequency equal to 1 kilohertz. Now, let me erase the board, create a little bit of space. Now, to solve this, we need to first chose one of the capacitance or resistance. It's easier to set the resistor as an input, so I'm going to consider R, which is both R1 and R2 equal to 15 kilo. Now, if I have 15 kilo of resistance and the cutoff frequency is equal to 1 over 2 pi RC, okay, and cutoff frequency I want to be 1 kilohertz. So this is 1 kilohertz equal to 1 over 2 pi times 15 kilo times C. If you solve that equation for finding the C, you would see that the C is going to be 10 nanofarad. Okay, so, and this is also C1 and C2. So now we have the values that we want for our filter. But you can see that we have two other resistors that we wanted to like set. Now, remember the feedback system in our op-amp is actually give us a gain for our circuit. So what RF and RG basically give us is the voltage gain, how much this circuit would amplify the voltage input and output, the ratio of output from over input, okay? And we can set that gain using the RF and RG. Now, we know that when we inject the input to the non-inverting terminal, the gain would be equal to 1 plus RF over RG. Okay? Now, I want to put RG equal to, again, 15 kilo. Okay? And I want the RF to be 22 kilo. Now, this is the reason that I choose RG and RF like haphazardly here, like based on what I like, is that I don't care. For this example, I don't care what is the AV. Okay? But if you have a specific AV in mind, you can choose the RG, and then using this, you can calculate the RF. For example, let's say it's 6. Okay, so if we want the gain of 6 is going to be 1 plus RF over 15 kilo, you still need to consider one of the values. We choose one of the resistors and then find the other. So this becomes, let me calculate, RF will become 5 times 15, which is 75, right here. Kilo. So if you want 6 for gain, okay, AV equal to 6, now your RF should be 75 kilo if your RG is 15 kilo. So now I don't care about this gain because I just wanted to show you how the filter works. So I just choose based on what I have in the lab. So I choose RG 15 kilo and RF 22 kilo. So if I have this, my gain is going to be 1 plus 22K over 15K. Let me calculate that. Okay, which is going to be 2.46, let's say 2.5. Okay, so this is going to be my gain. Now, let's go to the lab, actually build this circuit and see if it works. And we have the cutoff frequency and everything set to perfect situation. Now, before we go, actually, I wanted to let you mention one comment. In the cutoff frequency, okay, we want the gain of the whole system, so output to input, is going to include the effect of the filter and the effect of the amplifier. Altogether, we want the gain to become 3 decibel. Okay, which means 1.7 AV, the total AV. Okay, so it's going to be 1 kilohertz is going to be 3 dB, 3 decibel of the gain as a ratio of the output and input. Okay, now let's go to the lab and see if the actual circuit would meet our design.
Okay. In our circuit, I already put down the schematic into breadboard. So what I have is that I have 215 kilo to connect the input to the non-inverting port of my amplifier, of my op-amp. And I have a capacitor, okay, as a feedback between the output to the point between the two 15 kilo ohm resistor. I have another capacitor to connect the non-inverting terminal to the ground. Then I have the RF connected equal to 22K, and RG, which connects the non-inverting terminal to the ground, equal to 15 kilo. I am going to connect the input to the through the resistor that we talked. And as you can see, I already connected the VCC to the terminal number 4 and ground to the terminal number 11. My first channel, the yellow one, measures the input, okay? And the second channel, the blue one, will measures the output, okay? Now, I am going to inject a sinusoidal voltage with the voltage 200 milliamp, a millivolt peak to peak. So this is 200 millivolt peak to peak. And I'm going to choose a frequency of, like, for example, 500 hertz. 500 hertz, yeah, for an input. Let's conduct the input. And I'm going to connect the VCC. Let's tune the oscilloscope to see what's going to happen. Now, hang on. Okay. Now, as you can see, my input is 200 millivolt peak to peak, and my output is 1, 2, 3, 3.5 times 700 millivolt peak to peak. Okay, so it's about like let's say 4 times of the input. Okay, three something. Okay, now this is AV, not the decibel. Okay, don't mess up these two. Now, if I change my frequency to 1 kilohertz, okay, you can see that my output is changed. Right now, my output is 2 volt peak to peak. So it's 10 times bigger than my input. Okay, around 10 times, a little bit more than 10 times. Okay, now, if I one thing before I change the frequency. We set the filter at 1 kilohertz for the cutoff frequency. For 1 kilohertz at the cutoff frequency, we expect the gain to be 3 decibel. But as you can see, it's not. Okay, it's not 3 decibel. So that means that we are not exactly, the cutoff frequency is not exactly at 1 kilohertz. Okay, let's change the frequency to a higher frequency, like 2 kilohertz, to see what's going to happen. You can already see that the voltage is basically the gain of the filter is very low, very low. So it's basically attenuated the output signal. Now, let me see what is actually the output signal. Okay, now you can see that still the input is 200 millivolt peak to peak, and my output is also 200 millivolt peak to peak. So the gain is 1. Remember, our amplifier gain was 2.5. So it's already attenuating the signal. Okay, so the filter is working. Now, let's go higher. Let's go, for example, 5 kilohertz. Now, in 5 kilohertz, my output is 40 millivolt peak to peak. So it's basically 40 millivolt compared to 200 millivolt is 1/5, so 20%. Okay, so it is working pretty well. Let's go higher, 10 kilohertz. In 10 kilohertz, we barely see any signal. Okay, in 10 kilohertz, what we see is 10 millivolt in the output. Okay, so it's 20 times lower. So it's 5% of our input. So you can see that the filter is working pretty well. Now, you want to find out what is the actual frequency cutoff frequency is, because we already said that 1 kilohertz was not matching the 3 decibel gain that we have to have for the cutoff frequency. So you can change the frequency, measure the ratio, okay, and find out where you meet that 3 decibel. That's gonna be your cutoff frequency. Okay, you have to do try and error. Okay.
Okay, let's now talk about the comparator circuit that we are going to develop based on the op-amps. Okay, in the op-amp, we have, as we said before, we have 2 inputs, and the output is a linear function of the difference between the 2 inputs. We are going to use these characteristics of op-amp, okay, and set the inverting terminal as a reference value, and then use our input in a non-inverting terminal. So what's happened here is that if the non-inverting one is bigger than the inverting one, which is our reference value, okay, then we have a high voltage or positive voltage, okay, which means we have a high value in our output. And if our non-inverting voltage is lower than our reference inverting terminal, then we would have a low value in our output. So this is basically the concept of a comparator circuit using an op. Now, in the circuit that you see on the board, we have 2 op-amps and 2 sets of comparators. Okay, the task that we have is that we have a thermistor, which is a resistor that changes with the change in the temperature. Okay, and we want to see if for example, there is a warm value, meaning a certain amount of increase in the temperature, which means a certain amount of change in the resistor. Okay, we want to activate a yellow LED, and if we are going to the hot range, meaning there is a high range of temperature increase, meaning there is a high change in the resistance of our thermistor, okay, then we want to like activate the red LED too. Okay, so these double sets of comparator, okay, creates two indicator by comparing the input, which is the translation, electrical signal translation of the difference in the temperature, okay, compare it with the two sets of reference, one set to define the warm level and one set to define the hot level, and then turn on the LEDs based on the temperature. Now, let's look at the circuit, okay? Now, in order to translate that temperature into an electrical signal, more specifically a voltage, okay, we need to use a voltage divider between the VCC and ground, which divides the voltage between a constant resistor, we call it here R1, and that changing resistor, which is our thermistor. So when the resistor goes higher, the thermistor would have like a higher value, okay? The voltage here would change. Okay, if it has a lower value, also the voltage here would change. Now, we have to have two sets of reference. Okay, and we are gonna again use the voltage division to set the two reference. Okay, now we need, when we want to like use the op-amp to analyze how much temperature increased in your environment, okay, you need to set a threshold. Like for example, you want to say, okay, the room temperature is 25. If I go more than 35 degrees of Celsius, then I consider that as a warm. And if I go more than 40 degrees Celsius, I consider it as a hot. Now, you have to look at the thermistor to see in 30 degrees, okay, what would be the resistance of that thermistor and what would be the voltage division here. Okay, so you have to set the reference on that voltage. Same goes for the other comparator. So these two, R4 and R5 and R2 and R3, is basically defines the voltage division, which is equal to the threshold that you want to define the warm and hot temperature. Okay, now R6 and R8 are called pull-up resistor. They are here in order to provide a high voltage if the input is positive, meaning the non-inverting is bigger than the inverting. So these two resistors connect the output to the VCC, so it would pull up and make the output able to have like a high value. And then we have our LEDs, okay? We have our LEDs that if we have a high value, meaning we have a legitimate amount of current, which means that will be turned on, and we define that by this resistor. This is the current limiter. Okay, you have to also design the value for that. Okay, same goes for the other LED. If we have a higher, relatively a high level of current, this one will turn on. Okay, now for comparator circuit, we use the op-amp LM293. LM293 has two op-amps inside that chip. So now in this circuit, we want two op-amp, but both, so it using one LM293 gives us the two op-amp that we need. Okay, now how to read the ports of the op-amp? You need to be able to actually identify what is each of the pins. Now, when you look at the LM293, one part of the IC has a dot. Okay, that dot shows the pin number 1, and then you count from up to bottom 1, 2, 3, 4, and then here 5, 6, 7, 8. The right side goes from bottom to top. Up, down, down, up. Okay, so now the first pin, the pin number 1, is the output of the first amplifier. Pin number 2 is the inverting terminal, and pin number 3 is the non-inverting terminal of the first op-amp. Pin number 4 is ground. Okay, pin number 5 is the non-inverting terminal of the second op-amp. Number 6 is the inverting terminal of the second op-amp. Number 7 is the output of the second op-amp. And number 8 is the VCC. So this is how we could develop this circuit and implement this circuit using the LM293. Now, we are going to go to the lab, okay, and basically see an example of a comparator, actually a double comparator, and see how it works, okay?
Okay, let's actually test the circuit to see how it works. Now, I already put the circuit together. So these two are my reference voltages. Okay, these are the voltage dividers for reference voltages. One is 1K, 1K, so it's actually divides the VCC in half. Okay, and I'm gonna set my VCC at 5, so it's gonna be 2.5 volt as a reference. Okay, and it will connect to the my yellow LED, meaning it's connect to the warm threshold. So I define my warm threshold as 2.5 volt. Okay, now another one is 600 ohm and a 1 kilo ohm, which defines the voltage division when you apply 5 volt, which define the voltage division as 3.2 something, around 3.2. So my threshold for indicating the hot temperature is 3.2. So 2.5 warm, 3.2 hot. Okay, and it's connected to the op amp that is activating the red LED. Okay, you can see, I think this is the yellow LED and this is the red LED. Now I have my LM293 in the middle of these chaos of jumper cables. Okay, now these two resistance, you can see these two resistance here, this one, this is the pull-up resistor that I choose in order to basically make the output able to have like a high value. And it's connected between the output of each of the op amps and the VCC. Okay, now I didn't use the thermistor, so instead I use a potentiometer. Okay, it's the same. You change the temperature. The by changing the temperature in thermistor, the resistance would change. So by potentiometer, I can also change the temperature. And it is doing the voltage division. Okay, it's connected between the VCC and it's go through that. We go through the potentiometer to another 600 ohm resistor all the way to the ground. So the voltage division for our variable resistor is our potentiometer, between our potentiometer and that 600 ohm constant value. Okay, and I already told you how you can connect the pins in. Let me see if I have the LM3. Yeah, I hope you can see the dot. Can you see the dot? This is the dot in top. Yeah, now we can see it. So the pin, the left side, this one, the first one, the top one is pin number 1, then 2, 3, and the bottom one is 4. Okay, so the 1 is the output of the first amplifier, then there is an inverting input, then non-inverting input, then the ground. Now here on the other side, in the other side here, we have the non-inverting terminal at the bottom for the second op amp, then inverting terminal for the second op amp, then the output of second op amp, and the top one is the VCC. Okay, so this is how you can connect the terminals to your circuit. Now let me connect my voltage source to my circuit and turn it on. It is 5 volt. Okay, now rising the temperature, or like changing the temperature, not just rise, changes the voltage in a potentiometer. So let me change the voltage. Okay, something is disconnected. Let me check if I messed up one of the connection when I was showing you all the stuff. Oh, shoot. Check the polarity. I made the mistake. Okay. Now, you see, when I increase the value, after a certain point, my warm LED is gonna be turned on. Okay, now I'm gonna change that, and you see after another threshold, after another threshold, my hot indicator would turn on. So this is how an indicator using a LM293 as a comparator circuit can indicate and measure or compare a certain input to the reference voltage that you defined. Okay, that's about it. So uh, this is the end of our assignment. So thank you. And next we are going to talk about the other assignment.